Hello. So the second speaker of the day will be Professor William Duke. I don't think it's anything I'm doing. Okay. He's my advisor. Okay. So the second speaker will be Professor William Duke from UCLA, formerly Rutgers, lecture on analytic theory of automorphic forms.
Well, I'd like to thank the organizers very much for inviting me to speak today. So my general aim in this talk is to illustrate and motivate the use of analytic techniques on automorphic forms and their associated L functions. In particular, I'm going to concentrate on two main ideas or directions, which are the Ramanujan conjectures for L functions, for the coefficients of L functions, and convexity breaking for L functions. One of the themes I want to concentrate on is to illustrate that even though there are fundamental conjectures about what should be true for these issues, sometimes just obtaining a non-trivial result toward what should be true actually has qualitative consequences, which are interesting, and I want to illustrate that. In particular, the type of application I'm going to use to illustrate this are the existence and distribution of solutions to Diophantine equations, and in particular quadratic forms, although there are some higher degree examples as well. And I want to show the methods that have developed to do this, and they kind of go under the name of using families and the amplification method. So I'll start off with one of the classical motivations for the theory of automorphic forms in the first place, which is quadratic forms. And in particular, if Q of x is an integral quadratic form in m variables, one of the basic problems that's an ancient problem associated to such a quadratic form is to describe the integers which are represented by the quadratic form for integral values of the variable. And by the way, this makes sense over a number field, and I'll return to that issue later, but for now, I'll assume things are happening over Q. And in particular, if you look at the quadratic form over Q, one has essentially the perfect answer given by the Hasse-Minkowski theorem that an integer or rational number is represented over the rationals, has global solutions if and only if it has local solutions for every prime, for every place in general over a number field. So this is the famous local to global principle of Minkowski, generalized by Hasse to number fields. And but the quadratic form, automorphic forms really enter the picture when you look at this question over the integers. Then it becomes a much harder problem. And in particular, however, it's been one of the achievements of many mathematicians over a long time, but a fairly recent achievement that we can say that in 3 or more variables, a local to global principle does hold. But there's a provision that you have to assume that n is sufficiently large. So this analytic term plays a crucial role. So I'll try to explain this further. Well, for m is equal to 2 for binary forms over a number field, then it's not true that there's a local to global principle, but the underlying the class field theory is what you can use to describe the integers that are represented. However, you can certainly say that it's not understood at all. It depends on what you mean by understanding it. It's understood what the structure is that's controlling it, but it's not understood, concretely which integers are represented by a particular binary quadratic form. It's not represented in the sense that there's not a local to global principle. And if you take more than three or more variables, if you take 5 or more variables, this turns out to be fairly doable problem. It was approached by Hardy, Littlewood, and Klosterman, and there, the techniques that I'm going to describe essentially become trivial. It's not completely trivial, but suffice it to say that the case of 3 variables and 4 variables are by far the most interesting for this question and most difficult. And you can see the entrance of automorphic forms directly. Jacobi apparently essentially did this by attaching to let me assume first that n is 4 and that q is positive definite. Then we can associate to the quadratic form the theta series given by summing over all the integers, all the vectors in Z4 of the exponential function, and I use the standard notation E of z is e to the 2 pi I times z, of z times the quadratic form value. And I'm assuming here that z is in the upper half plane so that this converges. And the reason that this is relevant, of course, is because if you collect together the alphas that have the same value of q, then that counts the number of solutions to q of alpha is equal to n. So if you make it into an ordinary Fourier expansion, then it's a generating function for the number of representations of the integer by n. In particular, if rq of n is positive, then the integer is represented. So the basic idea, and its Poisson summation formula in this context, is that this is a holomorphic modular form of weight m over 2 in general, and for quaternary form, it's going to be of weight 2 for some level, and the level is determined by the quadratic form. So it is a modular form, and the old idea of Hecke is that as a modular form, if we understand the structure of the space of modular forms, we can decompose this theta series into a trivial part, well, not so trivial, the Eisenstein series, a linear combination of Eisenstein series, which kill its behavior in the cusps, plus a problematic term, which is a cusp form, which vanishes in the cusps. And the beautiful thing is that this linear combination of Eisenstein series, when you compute the coefficients, you actually compute which linear combination it is. The Fourier coefficient of the Eisenstein series has a local interpretation. It's a product of local densities of the representation of the integer by the quadratic form. But anyway, so the remainder term is the cusp form. It's actually a linear combination of what you would want to call a cusp form because they're not in general. It's not in general a Hecke eigenform, but we can decompose it into new forms. And as I mentioned, so the amazing fact is that if you have local representation integrally, well, since I'm talking about 4 variables, it's a little problematic, so we want to assume that we have local representation, which is primitive also, just to take care of some counterexamples if you don't have this. But if you have local representation for all places, then this coefficient rho of n is not only positive, but it's bounded by a power of n, any power of n less than 1 that you hope to choose, with a constant here which is explicitly computable. So it's about n, that's the way you should think of it. Well, so then obviously the issue that arises is, what about this linear combination of cusp forms and its coefficient? And it's clear that if we can beat n to the first by an explicit power, sliding around, so if we can obtain an estimate for the coefficient of the cusp form, which is a power less than 1, then we can conclude that for large n, sufficiently large n, the main term dominates, and the main term is positive if we have local solvability. So we can conclude the existence of a solution. And not only that, but a rough estimate for how many there are. And that, like I said, it's a marvelous fact that this rho of n, and this was first discovered in the context of the circle method, that much more generally, that this rho of n measures for you locally how well represented it is for each prime. It's a product of measures. Oh, okay, so a very old example of Jacobi is if you have a sum of 4 squares. It's the first case you'd want to look at. And of course, when you have small levels, then it may happen that there's no room for cusp forms, and that's what happens here. So the cusp form contribution is not there. So everything is the Eisenstein series, and here it has a particularly elementary formula for the rho of n. It's just 8 times the sum of the divisors, which are not divisible by 4. And you can see from that the size of that term. It's about n. In this case, you don't need even this epsilon at all to deal with this. But so in that case, you have a perfect answer. But of course, in general, you will have these cusp forms coming in. And actually, Klosterman made a huge breakthrough in this problem in the sense that he refined the circle method of Hardy-Littlewood, which doesn't allow you to beat the estimate n to the first directly. It gives you n to the first, and that's it. Just if you, and I'll call that the trivial bound. If you don't do anything other than look at the circle method directly. But he had a beautiful way of collecting together the various contributions that come in the integral in the circle method and produced Klosterman sums from the circle method. So he reduced the problem of producing a positive delta to estimating a Klosterman sum, so SMNP, which is a sum over x mod p of e to the mx plus x bar over p, where x bar is the inverse mod p. Well, he reduced it to this for general C here, but then by multiplicativity properties, the issue comes down to estimating the Klosterman sum for a prime. And he actually obtained the non-trivial estimate. The trivial estimate is p because there's about p terms. So he obtained a non-trivial estimate, p to the 3/4 for this. And that solves the problem, the qualitative problem of representation, because any estimate works. And so this was a beautiful, an amazing contribution to the subject. And the way he did this was he used his 10 fingers. So what he did is he took the sum of the 4th power of the Klosterman sum and actually evaluated it. It's something that you can actually explicitly evaluate. And it's a cubic polynomial in P. And then he observed that, well, these are positive. So even though I have a bunch of them, if I have an asymptotic formula or an exact formula for this sum, I can deduce from that an estimate for each individual term. And since we have a 4th power here, you can take the 4th root. So that's how he obtained p to the 3/4. Of course, that's not the end of the story. Then this Klosterman sum became an object of interest in its own right, and they, as an application of the Riemann hypothesis for curves, actually proved the best estimate for the Klosterman sum, which is square root of p times 2. And that, of course, gives you a better estimate for the cusp form contribution to the quadratic form problem. So I'll use this language that it allows this delta to be chosen for anything less than 1/4. Okay, so that's sort of the end of the story for the Klosterman sum as far as its bound is concerned. Now, when you introduce the theory of L functions, as Hecke did for this type of problem, then if I assume that f is a Hecke eigenform, then we can look at its L function, and this is very familiar, but so then the L function will be a product of local L functions, and in this case it's a degree 2 L function, and these parameters alpha 1 and alpha 2 will have the property that their product is 1, and the sum of their trace times p to the half, which is coming from the weight term, will be our coefficient a of p. And in a slightly different context of the delta function, the Ramanujan conjectured that, in fact, the alpha p should be bounded by 2 root p, the AP should be bounded by 2 root p, or that equivalently the absolute value of the alphas should be 1. And if you have this, then you get essentially the best answer for the cusp form estimate, which would allow you any delta less than 1/2. So we're going 8 So Klosterman, by the way, gives you an eighth, and this gives you a fourth, and then finally a half. Okay, well, so the Riemann hypothesis in this case for the L function, the local L functions, was due to Eichler because this is a weight 2, and then for general weights it's Deligne, and so this is one of the few cases where Ramanujan is known, of course. Okay, there's a related problem, which is sort of an extension of the representation problem, which is, well, what if I know I have a bunch of solutions? How can I describe how they're distributed? How are the integer solutions to the quadratic equation distributed? Well, what do I mean by that? Well, for example, this becomes an interesting problem even for the sphere, where the quadratic form is as simple as possible. You can do this for any quadratic form as well. But what one can do with a positive quadratic form is project the solution down onto the sphere. If you have a solution, project it onto the unit sphere, so divide by the square root of the length. And the problem then becomes to show that the solutions for a particular n, when it has solutions, well, for 4 squares, there's always solutions. When it has solutions, how are those points distributed on the sphere as n tends to infinity? This should be distinguished from the problem of looking at all the solutions for n less than an x. In other words, the circle problem, where you count all the lattice points inside the circle. Now we're taking lattice points of a given length and projecting them on the sphere and letting that length go to infinity. And here, it's a perfect setting to apply classical harmonic analysis, because what one needs to look at are the, for a general continuous function phi, you'd want to essentially form the Riemann sum of the points that you're interested in looking at the distribution of, dividing by their number, which is R4 of n, and proving that that tends to the integral. That's really what we mean by uniform distribution, where this is obviously Lebesgue measure on the sphere. And, well, so harmonic analysis says we can harmonically decompose any nice function into spherical harmonics, so let's use those instead. And the beautiful thing about that is, well, a couple nice things happen. Well, for one thing, this will be 0 unless the harmonic is trivial, unless it's 1. And then for another thing, if we make the analog of the theta function with these as the harmonic function as the coefficient, then that's actually still a cusp form. Or that's a modular form. And in fact, it's a cusp form if the degree of the spherical harmonic is bigger than 0. So a spherical harmonic in this case is simply a homogeneous polynomial, which is a harmonic polynomial. Those give you the harmonic analysis on the sphere. So, well, the fact that this is a cusp form, and you can see that the coefficient of this, if you collect together the alphas which have this q of alpha equal to n, give you exactly the left term, well, without the 1 over r4 to the n. So if I want to show that this is true, then what it reduces to is showing that the left-hand side tends to 0 for non-trivial phi. This is Weil's criterion in the case of a unit circle. And, well, we can handle it because the coefficient, they are the coefficients of a cusp form. Well, now the weight goes up, of course, with the degree of the spherical harmonic. However, it's easy to check that any non-trivial bound toward Ramanujan gives you that this tends to 0, and hence gives you the equidistribution of the points. So that's another example of where getting any non-trivial bound gives you some qualitative information. Well, I alluded to the fact that 4 variables and 3 variables are the most interesting. And in fact, 3 variables turns out to be quite a bit harder than 4 variables. And you can see this for a number of reasons. But the main reason is because what we have to estimate for this problem, we still have the same general setup. We can decompose the theta series into Eisenstein series and cusp forms. But the issue now is that the cusp forms are half-integral weight, with weight 3/2. So the theory of Heck operators only applies to square classes. It doesn't apply to square-free classes at all. So there's no hope of using a direct Ramanujan type of estimate. However, beautifully enough, what is replacing Ramanujan in this setting is exactly estimates of L functions at special values. So this was something that's been observed in different contexts, but so what replaces Ramanujan are non-trivial estimates for L functions. So an old application of this, old now I guess, is that for a positive ternary quadratic form, one can represent every sufficiently large square-free integer provided it's represented locally. And in a very concrete version of that is that it has to be represented, that n has to be represented modulo a particular integer, d squared, where d is the discriminant. So this is a very concrete version of the local to global principle for n sufficiently large. And the sufficiently in this theorem has the annoying property that it's non-effective. So this is I'll return to this later. It's a stumbling block. Now this theorem was originally proved using sums of Klosterman sums, using estimates for sums of Klosterman sums. However, it's evolved to the point where it's best seen now in the family of such problems as being an example of convexity breaking, which is something I'll return to in more generality. Let me speed up here. So the entrance of the L functions into this type of problem is already seen with a simple example of sum of three squares. If you compute the Eisenstein series coefficient, it's everything in this case. And we have a classical formula due to Gauss that the number of representations of n by 3 squares is actually given by a special value at 1, not a central special value, but a special value at 1 of a classical Dirichlet L series with these constants which are detecting conditions modulo powers of 2. And chi of n is the classical Legendre symbol, or Kronecker symbol in this case. So you can see that this is not a multiplicative function in n. You can already see that there's something strange going on here, something different. It is an Euler product, so it is a product of local densities. But and also the lower bound, which I indicated for 4 variables, becomes much more problematic here because L1 of chi is a class number essentially, and I multiply it by the square root of n. So R3 of n is essentially a class number of an imaginary quadratic field. And so to get a lower bound for that, thank goodness we have Siegel's estimate, which gives us the correct order of magnitude, essentially up to an arbitrary small power of n, so n to the half minus epsilon, and this is the non-effectivity which enters. And I like to make a point here that if an arbitrary epsilon can be chosen, there is a constant, you can't compute it. However, you have to, in order to beat this, in the bound for a of n, you have to obtain a power savings. Nothing which was sort of tricky, for example, saving logs by using compositeness or anything like that is going to be enough to get a non-trivial estimate. Okay, well, the relation to L functions is pretty direct in this setting. It comes from Waltz-Brzez's theorem. And so for the cusp form contribution, it comes down to estimating the twist of the L function associated to an integral modular form via the Shimura lift. So f is an integral weight modular form twisted by a Dirichlet character, but it comes down to estimating once again in terms of n, where chi of n is the same Dirichlet character. So it's L1 of chi of n, and at the central point, it's L of a twisted cusp form of weight 2 at the central point. And so the method of families has evolved to give estimates for this type of L function special value. Now, I want to say that if you look at this over a number field, the question of representation of integers by quadratic forms over number fields, this is Hilbert's 11th problem. And if you have 4 or more variables, an algebraic approach works beautifully for this problem. And in this case, Kneser proved that you have the same type of integral local to global condition over number fields in 4 or more variables. He is using an extension of the Hasse principle fairly directly. However, for 3 variables, the algebraic approach still doesn't seem to work. And if you try the analytic approach directly over a number field, those of us who have tried this over the years understand that that's often easier said than done. And in particular, if you try to make the circle method work, which Klosterman actually did, you run into grave difficulties with doing the Klosterman leveling refinement. And the circle method essentially breaks down over number fields. Formally, you can do it, but it doesn't lead to the estimates that you need. And once again, the most difficult case here in the ternary case is when you have a positive form over a totally real field, so a totally positive ternary form over a totally real field. And remarkably, very recently, Cogdell, Piatetsky, Shapiro, and Sarnak have proved that the integral local to global principle holds here also, so over an arbitrary number, over a totally real number field. And as I said, it's still non-effective because one still has the entrance of a Siegel zero problem entering into it. So I'll return to this, say some words about how this extension was made. Quickly mention for indefinite quadratic forms, most of the interesting problems are about equidistribution. The representation problem is typically easier with an indefinite quadratic form. But one big difference is that non-holomorphic or Moss forms enter the picture fairly directly. If you look at, even in 4 variables, if you write down the determinant equation, you can see easily that this is going to lead to classical Hecke operators if you look at the distribution of solutions to this. And also, I'll mention that if you impose divisibility condition on one solution to this quadratic equation, where the congruence is large, so if you assume that x1 is divisible by large n, this leads directly to Selberg's eigenvalue conjecture, as has been introduced before. And I'll also mention that higher degree forms, indefinite forms like the determinant, can also be analyzed by using spectral theory on GLM. But once again, the ternary case is perhaps the most difficult here also. And here, for example, if you look at the discriminant equation, x1 squared minus 4x2 x3 is equal to n, then one can carry through the program and prove, for example, that solutions to this, when you place them in the hyperbolic plane, become equidistributed as the discriminant goes to infinity. And if you interpret it correctly, if you take the indefinite case, this also applies to closed geodesics for the modular group becoming uniformly distributed if they're ordered by their discriminant. And I'll mention here that a very recent developments of this, if you have a totally real field, Zhang has pointed out that some cases of the Andre Oort conjecture come down to a similar analysis of breaking convexity, but now for Rankin-Selberg L functions, which are beyond the reach, but are very tempting. So there's a very interesting problem here to break convexity. And he has some results which actually do generalize directly this result, but one needs some refinements to get this conjecture. Okay, so let me introduce the general Ramanujan conjecture. So if we have L functions on GLM, and here I don't think I need to spend too much time except just to fix the notation. So I'll talk about them over a general number field K, and let A be the Adel ring of K, and suppose that pi is a cuspal automorphic representation of GLM of A with a unitary central character. So the L functions of great interest here, of course, are the standard L functions, which are a product of the local L functions. So I use this lambda instead of L for the complete L function because it's nice to distinguish the finite part from the infinite part. So for the unramified places, then these are given by polynomials of degree m, the degree of the L function, and determined by the local information of these Taka parameters, at least for unramified guys. And at the infinite place, these are products of gamma functions. And the two different gamma functions depending on whether we have real or complex embeddings. And I will call LS pi the product over the finite primes, because that's a Dirichlet series. And so for some issues, it's very important to distinguish the Dirichlet series from the gamma factors, or the finite factors from the gamma factors. So these are wonderful L functions, and we know essentially everything we know about, not essentially, but many things we know about the Riemann zeta function and the Hecke zeta functions and GL2 zeta functions are known for these guys, but due to Godemont-Jacquet. So for example, the lambda is entire, except when m is 1 and pi is trivial, where we have a Dedekind zeta function. And we have the standard functional equation relating lambda of 1 minus s to lambda of s with the conductor, a positive integer, and this mysterious root number, which has got absolute value 1, pi hat the contragradient representation. And after Langlands, it's expected that every L function, every decent L function is actually a product of these guys. That these guys could give us everything ultimately, even over Q. But it's convenient to actually use them over number fields for certain things that I'm going to discuss later. For example, the generalized Ramanujan conjecture in this context is that for unramified places, once again, the alphas should have absolute value 1, and the real part of the mu's, which are in the infinite places, should be 0. So this reduces to the Ramanujan in classical cases. And it's only known, as far as I know, for holomorphic forms when m is 2. Well, when m is 1, it's known. But when m is 2 and k is q due to Deligne, and as in Taylor's lecture, there are some other cases which are known now. Mention again, I think Shahidi mentioned this, but when k is q, the infinite place Ramanujan conjecture is equivalent to the Selberg eigenvalue conjecture about the eigenvalues of the Laplacian for congruent subgroups. Well, when you approach Ramanujan, I hope I've given some motivation for why you might want to obtain something toward it, even if you don't have the full result. And, well, in particular, Jacquet-Shalaika pointed out that just the local bounds directly for a cusp form already give you some interesting information. So these are the base estimates, that the alphas are bounded by the norm v to the half for finite, and that the real part of v is bounded by a half for the Archimedean places. So these are the base estimates, which I think I'm missing should be mu. So the problem here is to beat this estimate, and so obtain any delta strictly positive so that for unramified places you beat the exponent by delta. Of course, you'd love to have delta to be 1/2. Well, unfortunately, we can't. Well, the best known general result is due to Luo, Rudnick, and Sarnak, and they have that delta is 1 over m squared plus 1. Now, there's been lots of work. I'm not going to recount all the results, but suffice it to say that when m is 2, one has the machinery of symmetric powers and all the beautiful work of Shahidi and Kim. And for that case, one has delta is 1/9, which is significantly better than this. One thing I want to emphasize about these estimates is that they're uniform in the degree of the number field. And for an analytic number theorist, this is sort of an astonishing thing, because if you try to compare, for example, Dedekind zeta functions to the Riemann zeta function, if you're interested in very classical problems like the behavior on the critical line, if you understand Dedekind zeta functions uniformly in the number field, then you understand powers of the Riemann zeta function, and you have everything that you want. However, for the Ramanujan conjecture, it's turned out that you get such uniform estimates. And Shahidi observed this like 10 years ago when he got an estimate 1/5, which is uniform in the number field. And it's really, for an analytic number theorist, it's really an astonishing thing, the uniformity in the number field. In fact, to nail this down, let me point out that the straightforward analytic approach to getting estimates is to use the is to use the Dirichlet series part of the L function directly, but for the Rankin-Selberg, this is the usual way to go, and because the coefficients are non-negative. So if I take the Rankin-Selberg L function, well, thanks to Jacquet, P.S., and Shalaika, it has known analytic properties. I won't go into the details of everything, all the details of what's known, but it's enough to apply a classical lemma from analytic number theory. Landau, it's usually called the Landau lemma. It's Perron's method together with some cancellation of exponential integrals. So one can obtain an asymptotic for the sum of the coefficients of the Rankin-Selberg, which of course are directly related to these parameters we're interested in estimating, at least at the finite places. Yeah. Oh, yeah, okay, yeah, you're right, thank you. Yeah, silly me. Is that it? I can't do arithmetic, especially not now. Okay, so the Landau lemma, in this case, the crucial thing here is we get an asymptotic. There's a pole at 1 for the Rankin-Selberg guy, and we get an estimate for the error term. And this comes from basically an exponential integral, cancellation of an exponential integral. And so, but the crucial thing to notice is that the error that you get, it depends on quotients of the gamma functions. The complexity of the integral depends on the gamma functions. The more gamma functions you have, the worse the estimate gets. Well, when you have m, you have m squared from being GLM, and you have d from being a degree d number field, the estimate gets quite bad as either one of these gets big. So, well, one can observe that you can get delta is, I hope this is right this time, 1 over d m squared plus 1. Sarah observed this over q, led to 1/5, for example. But this is definitely not uniform in the number field. So you can see that this method doesn't work well for number fields if you want uniformity. Well, there's been one technique that was developed for overcoming Landau's lemma is to try to obtain more flexibility in what you're going to twist by. If you think about Landau's lemma, what you're using is you're using the t variable. When you do this contour integration trick of Perron, you're making use of the t variable or the s variable along a vertical line. But that's kind of limited, especially when you have higher degree L functions. You need more flexibility. So it's turned out that the method of families is to try to introduce an appropriate family of L functions. I mean, you can think of L of 1/2 plus IT as being a different object than L of 1/2. They're sort of, they're related to each other as numbers. But so instead of twisting by t, we'll twist by other things. And the most elementary thing to do is to try to twist by characters. So for example, over q, this was done by myself and Ivanic. What one can do is, instead of using the gamma factors in Landau's type lemma, one can make use of the root number, the finite gamma factors, Gauss sums, and play a very similar game. So instead of doing contour integrals, we'll use Dirichlet characters to pick out progressions. And I'll try to go through this very quickly. So one estimates the difference between this. So Bn is the coefficient of the Rankin-Selberg L function. And if you use twist by Dirichlet characters, you can pick out arithmetic progressions modulo a prime p. And if we sum up over n about L, this means n is in a range between L over 2 and 2L. And we subtract off the expected main term, then it turns out that when you compute that, what you're doing is you're left with an exponential sum, which is a Deligne-Klosterman sum, which plays the role of what you get in Landau's lemma, which is an exponential integral. Of course, estimating this is much harder than an exponential integral. But happily, we have Deligne's estimate for this hyper-Klosterman sum. And what it leads to is an estimate for this delta, which is in terms of p alone. And the crucial idea was, well, we have lots of different conductors, so we have to use all the characters modulo a lot of different primes. And when you add all those together, and you make use of the fact that if n is equal to L, then n minus L is divisible by every prime. That's a crucial fact. So the term that you're interested in is repeated. And the fact that it's repeated allows you to get an estimate for the individual term. No positivity is used here. But anyway, you rederive the same bound over Q, in this case, that you get from Landau's lemma. However, since it doesn't require the coefficient to be positive, it's been used in a number of cases where one can reduce the number of gamma factors by taking, for example, the symmetric square instead of the Rankin-Selberg and get improvements toward Ramanujan. However, it's turned out that as the method evolved, it was discovered that the flexibility in twisting was the really crucial thing. And it was found by Luo, Rudnick, and Sarnak. They're not using exactly this method, but philosophically, it's related to this. They're able to use a development of this to treat, first of all the places at the same time, not just the finite places. So they look at the L function instead of these partial sums. And they're also able to treat arbitrary number fields. But this required a very non-trivial extension of the Dirichlet character method, because the problem is there's not enough array class characters to do the job. But they use a construction which is due to Rohrlich, which allowed them to do that. Okay, now let me switch to convexity breaking for L functions. Now here, of course, the main problem, the main unsolved problem about L functions is the Riemann hypothesis, that the zeros of lambda s lie on the line real part of s is equal to half. If you know that an L function is got this usual properties of an L function, that it's holomorphic and has a functional equation, well, in some sense, the fun has only begun, or the pain, depending on your point of view. So it's not the end of the story, and I'm sure GRH is also not the end of the story, as work on distribution of zeros has shown. But of course, we'd love this to be true. We think it's true. But if the point is that even though we don't know this is true for any single non-trivial global L function, we can still try to approximate some of its consequences. So to describe this, I'll define the analytic conductor of this representation pi. This looks complicated, but it's got the arithmetic conductor here, and then it's got a product of factors which are controlling the size of the representation. So it's got the gamma factor parameters here, it's got the t variable here, the degrees, depending on whether the embeddings are real or complex. So think of it as just measuring the complexity or the size of the representation. And for estimation purposes, the Lindelof hypothesis is probably the correct thing to look at, and that says that on the critical line, the L function should be bounded by an arbitrarily small power of this analytic conductor, uniformly in all these variables. And the reason that you expect this to be true is because it follows from the Riemann hypothesis, for example. But along the lines of what we said about Ramanujan, there is a somewhat trivial bound which follows from knowledge of the analytic properties of the L function, namely that it's bounded by what the Fragment-Lindelof principle gives you by convexity, by the convexity principle. And that's that the L function is bounded by the conductor to the 1/4. So think of that as the base estimate for what we're interested in. And the subconvexity problem is to, once again, replace this exponent by some exponent strictly less than 1/4. And I should say in the applications, for example, the ones that I started the lecture with, typically you only try to obtain such a bound in terms of one of the parameters. You don't try to do them. It can be very hard to get good estimates in several of the parameters. What am I talking about? Well, for example, the t variable or the parameters in infinity that in the gamma factors, those would be different aspects, or especially the arithmetic conductor. It turns out to be the one that has perhaps most of the arithmetic applications. So for example, in the applications to quadratic forms of ternary quadratic forms, it comes down to L of a half of pi twisted by a Dirichlet character. And here, this character, the dependence on n is the crucial thing. Of course, if you start twisting a representation by a character, so it's in this case, it's a GL2 twisted by a GL1, the conductor is what's increasing as n is increasing, and it's increasing in a completely explicit way. I will mention that the other aspects are also interesting for breaking convexity. In fact, there's a growing number of examples of where convexity breaking gives you something interesting. For example, if you look at the infinite places, so if you look at the eigenvalue aspect, then there's a nice conjecture of Rudnick and Sarnak that classical Moss forms, as the eigenvalue goes to infinity, become uniformly distributed, meaning the mass becomes uniformly distributed. Now that turns out to be a very tricky problem, but it reduces to a convexity breaking problem in view of a lovely identity of Watson, which relates, plays the role of the Waltz-Purzay theorem and relates the Weyl sums that arise for this problem to the special value of a triple product special value. I won't say much more about that, except that it's an open problem and very seductive problem there, which appears to be very hard. Well, over Q, the convexity problem has received a lot of work. In the level aspect, there's a series of works by myself, Friedlander, and Iwaniec, which give various convexity breaking estimates, not just for twists, but in terms of the level itself. For K totally real, as I mentioned, Cogdell, Piatetsky, Shapiro, and Sarnak have generalized this type of result and were able to get it uniformly over number fields. I will mention that even in the very classical case of K is Q and M is 1, so we're talking about Dirichlet L functions. Some of the hardest problems are here. Conray and Iwaniec have recently improved the original convexity breaking theorem for L functions, which was due to Burgess. So for estimating Dirichlet L functions on the line 1/2. And they do this seriously using GL2 L functions and twists. A quite remarkable paper. So for those of you who know exponents, they have 1/6. So what does that mean? But it's quite a nice argument. And there are some higher degree cases that have been successfully treated. Kowalski, Michel, Vanderkam have succeeded in doing this for a Rankin-Selberg inner product, which, by the way, that's what the uniform distribution of mass comes down to, but where pi 1 and pi 2 are holomorphic, and one is fixed. If you fix one of them, it turns out to be still doable by current technology. All right, now let me say a few words about the amplification method and the philosophy behind it. Now, one of the difficulties in analytically treating an L function is that, well, you can, if it has a functional equation and nice analytic properties, you can approximate its special value, say at 1/2, of course, by a morally speaking finite sum. So what I have here is a sum over the coefficients. This W is a smoothing function, which essentially picks out. So I'm doing this in general, so n is an ideal in the field that we're talking about, and norm of n is the norm of it. But such a sum is controlled by x. That controls how long the sum is. And typically, the bigger the x is, the more out of luck you are. And, well, okay, so in this case, you can choose, because of the functional equation, you can choose x to be about the square root of the conductor. So the bigger the conductor is, the harder the problem is. Now, you can see from this, you can get the convexity bound, which more directly, in fact, from such an approximation, if you know something about the bound for the coefficients. Well, if you know Ramanujan, that makes it very easy, but it turns out you don't need to know Ramanujan to handle this type of sum. You need to know something on average. So, in fact, you can handle this on average well enough to estimate this directly and recover the convexity bound. The whole game is to go beyond the convexity bound. So one technique which has evolved to do this is to try to find an appropriate family where we can average over this family and then by restricting to one term, obtain a non-trivial estimate. The same theme that Klosterman started, so except in the context of L functions. Well, so what one does is one needs to find a family where it turns out the conductor should be about in the same range. I take the mean square of the L function. And a guiding light here is, what would the Lindelof principle give you? Well, if you average, the whole point of averaging is that you hope that you can make something which is intractable more tractable. And that turns out to be the case. So if you assume Lindelof for what you're really trying to get at, well, then you can guess what this sum should be. So it should be bounded by the number of elements in the family times the conductor to the epsilon. And in fact, you can obtain that, not as a conjecture, but you can prove it, provided your family is rich enough and has enough orthogonality and is big enough. Okay, well, so the size you need, unfortunately, or I mean, if this wasn't true, then there'd be something wrong. But so the size of the family is the square root of the conductor, which typically allows you to do this not trivially, but softly. Amplification is a method which was introduced by Friedlander and Ivanich for the purposes of Dirichlet L function originally, which is to introduce an extra mean square term, which has the effect, one way you can think about it is it's arithmetically shortening the family, making it smaller. A little hard to intuitively see that, but if we can obtain such a bound where we have another finite sum where the alpha of L's are actually arbitrary complex numbers. And the range of this is to be thought of as being extremely small. We just want to get a little bit of improvement. And if we can obtain a bound like this, which is the number of elements in the family times y, which is the length of the sum, times x to the epsilon, if we can do that, then with the choice of these coefficients being equal to the conjugate of the coefficients we're starting with, this becomes an amplifier. It plays the role that it becomes a large term which I can divide out and obtain a result for an individual term which it proceeded to amplify. So I choose alpha of L to be b sub pi sub 0, where pi sub 0 is the guy I'm interested in. He will be amplified. And the key feature in this, where all the difficulties arise, is because once you do this, off-diagonal terms arise. And in a sense, when you have the family being big enough, when it's soft, it's because everything is in the diagonal. The orthogonality is just enough. But if you want to do something deeper, you need to handle off-diagonal terms. And, well, without smoothing, they're roughly this. And such terms are very difficult to handle, and it depends on the family that you're looking at. You need to find an appropriate family where you can hope to handle such terms. I won't go into this too much other than to say that for the twisting part and for the level aspect problems over Q, for example, these reduce through spectral theory through the Kuznetsov formula to estimating Klosterman sums ultimately. Not quite that easy, but ultimately it comes down to the theory of Klosterman sums. Over a number field, it doesn't work this way. In fact, this is what Cogdell, P.S., and Sarnak discovered, that you cannot use Ray class characters directly because they have to be trivial on the units, and there's not enough of them. So what they found, it's quite a remarkable thing, they returned to Selberg's original approach to handle these things, which was through Poincaré series, to handle sums like this. You can think of this as being a shift. This is like b pi alpha, b pi bar of alpha plus h, with a large shift. Selberg introduced a formalism to handle such sums using Poincaré series, but for estimation purposes, there was a big problem, and Sarnak was able to actually find a solution to this problem. And in this case, and it also works over a number field, because he was able to discover that if you embed your characters in sort of what he calls fake twists, which are not Ray class characters, they're not natural characters on the number field, but nevertheless, they're still amenable to the analysis. So he makes a larger family than what the number field itself provides for you, and they were able to actually make that approach work, of the twisting approach work. And a nice feature of this is that actually the whole spectrum of GL2, including the Moss forms, enters into the analysis. However, the application, of course, is to holomorphic forms, to Hilbert modular forms, to L functions associated to Hilbert modular forms and their twists. And this is a phenomenon which we've seen over and over again, that actually to understand holomorphic forms, you need to understand the whole spectrum. This was seen by really many times in the subject. So I'll end with a question which is not directly related to the theme, but I think it's quite an interesting question. If you think about what's going on here, for GL2, it was clearly seen that for Ramanujan, the correct thing to look at are the symmetric power L functions. If we can understand the analytic properties of symmetric power L functions, we get Ramanujan. And that was the structural setting for looking at powers. Now, using powers in analytic number theory is a very old thing. I mean, if you want to estimate L functions, your first inclination is to estimate powers of L functions. The problem is we run into the same type of problems that you run into here. The fourth power is a sticking point, and it arises over and over again. And my general question is, is there an analog for L functions, maybe over GL2, of the symmetric power construction, which is the correct construction, which will allow the orthogonality on GLM to handle these problems like the Lindelof conjecture? Is there a setting? This is, of course, a very rhetorical question. I have no idea. But what seems clear is that the actual powers are not quite the correct thing to look at for that purpose. Although one can certainly conjecture what should be going on there, I suspect that the structure has not been found yet for actually studying higher powers of L functions. Oh.
Questions or comments?
Yeah, so density results about this, yes. Yeah. Yeah, it couldn't be complete at all.
Comments or questions? If not, let's thank the speaker for a great talk.